send out an email about what sections to skip. In terms of readings, what was that question about, or just the assignment? Okay, for the chapter summary. Yeah, I can certainly do that. Thanks for pointing that out. Cool. Yeah, so do join us tomorrow for our physics tea. It's it's a good chance to just hang out. Only doesn't take that much time. See some people, not just from your classes. And then hopefully you've been starting in on the homework. So we'll have that. Hopefully you've made some pretty good progress on that, but I'd like to get that on Friday. Likewise, the chapter 9 summary. The quiz number 5 is up as well. So for that, please get it done by Sunday. And wanted to check in with you folks for the final exam. It would be like the last two. I will try to get those to you next week. But the idea is to post it this weekend and give you, a good week to do it. Have it due, say, Sunday. That will, make it so it's, it's the weekend when there aren't a ton of other things scheduled, and it gives me time to get it graded and turned around, check in with you folks about things. Does that sound reasonable? All right. Material cover chapter 9. Yeah, so the exam is right. This final exam is kind of like an exam on the material since the since exam 2, plus an like a review, not review, like a retrospective. So about 2/3 of it is going to be the material that we've done since last exam, and so that's really chapter 9. So sections 9.1 through 9.4. And then, but there'll also be stuff on a little bit of everything that we've done. I'm going to try not to make it too long. Knowing how things are going. Although it'll take a little bit of work for sure. Okay. So like I said, today what I'd like to do is start out just giving us a quick overview of waveguides, and I'll tell you why in just a moment. But then when I say overview, it's really just talking about them almost qualitatively. It's in 7.5 under regular circumstances. We have time to do problems on it and like do some group in-class problems after going over it all. And nope. And then after that, though, we'll start in on talk about chapter 10, and gauge freedoms, because it's an important idea that's used as a basis of a lot of particle physics and things like that. So it's the origin of a lot of other things. So that's important. But I wanted to hit on some of the aspects about waveguides here, because they're actually there are two reasons. So first of all, they have technological applications. So we can use them for RF waves. They're used a lot for microwaves. It's the same idea behind fiber optics, and you can even use them in acoustics. So technological applications are useful. The other thing, and we're not going to get into this this year, but the reason why I feel it's useful to do them is another opportunity to practice separation of variables under normal circumstances. But we're not going to really do that right here. So what is a waveguide? Basically, it's a hollow pipe that, as the name suggests, it guides the wave. So what we're going to do in the textbook, they look just at pipes with a constant cross section. They don't look what happens when the pipe changes its shape as you go along it, or if it bends or things like that. They look at it as just like, okay, you've got a cross section, and then so you've got a certain shape in 2 dimensions, and then you just extend that forever in the 3rd dimension. So what we do typically is we're going to have simplest thing is the walls perfect conductors. Perfect. That's and so what that means is that you can't have any any parallel electric field on them, and you can't have any perpendicular magnetic field. And so the result of all this is that only certain waves are allowed. Basically because of these boundary conditions. So a couple things. They're not necessarily transverse. And how can that be? Well, before we had no free charges. Even when we had waves hitting interfaces and so on, right? It was just in a material and there weren't any free charges. Now, because we've got this conductor though, right, we can induce current and charges and stuff like that in the walls, particularly the currents. And so that means that we no longer have this restriction from our divergence of E equals 0, divergence of B equals 0. We no longer have those restrictions. It's the divergence of E being 0 when there's no free charges, and the curl of B only depending on dE dt when there are no free currents. But we can now, because of the presence of these walls, we can have charges and currents there. And so we can, in fact, have non-transverse waves. So, all right, that's one thing. The other thing, though, is if we have these if we've got these waveguides that look the same along one direction, let's call it the z direction, then what we can do is, and particularly if their cross-section has nice symmetry, right? That's the kind of thing that makes our life easier. So if the cross-section is like a rectangle or like a circle or something like that, then we could do separation of variables as a useful technique with our wave equation, right? Just like we did separation of variables techniques with Laplace's equation back in Fun 3. And what you get is propagation down the z direction. And then in addition to that, right, we have a component of our wave vector that is not just longitudinal, but is also transverse. But those you're only allowed to have certain values. And what you get effectively looks like a standing wave in the cross-sectional direction. And all right, so.
When you say separation of variables, are you saying that the waves can have y, x, and z components, and we're only concerned with the z?
Well, so the z, we are concerned with all of them, but we're going to separate them into the x, y, and z solutions, right? So instead of just having one big function, right, we can actually write it as a product of an x function times a y function times a z function, right? Because we've got this Laplacian that's separated, right? It's second derivative with respect to x plus second derivative with respect to y plus second derivative with respect to z, and the boundary conditions are lined up along our coordinates. So yeah, we can write, when I say separation of variables, we can write our, whoops, let me write this, all right, our E
So all the directions are independent of each other?
Not fully, but close to, right? We're gonna have things like where we've got a second derivative with respect to x is equal to some constant, and the second derivative with respect to y is equal to the negative of that constant, or something like that, right? They're tied. So what that's going to do is they're impose relationships among their wave numbers, right? But we can still write the independent function. So x of x and t, y of y and t, something like that, right? And actually, usually we can we can usually get rid of the t's, right? I'm sorry, I don't want to get rid of the z1. The z1 gives us the oscillations, the propagations, right? And so here if we make that the longitudinal direction, and these right here will be the transverse directions.
What if we have a wave with no z component?
So there are going to be limits, right? So first of all, that would just be bouncing along, and we're sure we can have things that just bounce around inside them, but we're going to be interested in guiding the waves down these tubes. So we're specifically going to look at the z components of these things, and we're going to find that there are only certain values that are allowed for their frequencies. Only certain frequencies give us the solutions. So here, actually, I'm going to let me just really quickly snip this, and I'm going to show you an example of what the transverse modes look like in a couple different situations right here. Oh, and so actually, what I should also say is. I'm going to add one note before I get rid of all this and take a picture. Sorry, let me just, I don't like that. Yeah, exactly. Right. So why is, we're only talking about, really long straight tubes, but so long as the bend isn't very rapid, we can say, hey, that looks like tubes. Right. So one of the things we're going to see is there's this cutoff frequency above which the waves don't propagate. I just said that. I just did that wrong. It was the wavelength above which the cutoff frequency is below. And actually, the easy way to think of this is if the wavelength gets to be, comparable to the cross section of the waveguide, then you can't fit the wave in there. Really, it's coming from mathematical solutions, and there's, what you get, and you can still send that wave in, but what you get is an imaginary wave vector, so the wave just attenuates away. Right, and we're interested in propagating these down through these waveguides for, usually because we want to use them to literally guide waves from one place to another. And actually, all right, before we do that, let me do one more thing, and then I can snip it all together. So let's imagine like we're looking at, still confused about driving, but boundary conditions. Oh, well, we have the boundary conditions, right, is that you can't have any parallel component at the boundary, right? Because it's a perfect conductor. You can't have a field inside the conductor. You can have a perpendicular component of the electric field because that's stick pointing away from the boundary. It's like having some charge on the boundary. The field can point away from it, but you can't have a field that points in because it would then induce an infinite. And same thing for our magnetic field, except with a perpendicular component. Oh yeah, yeah, totally. This is all about interference. Yeah, yeah. So that we're looking at chapter 2, conductors. In a perfect conductor, you can't have an electric field in it. If it was a non-perfect conductor, you can have some electric field. But we're taking this the ideal situation, or where the conductivity is big, that we can approximate it like that. So here we've got this. I'm going to make this a really long wave right here, and it turns out that the different frequencies have different speeds. Right? What about the EMF in the conductor? Yeah, I mean that's what it's all. You mean in irregular wires and stuff like that? That is, yeah. So we have the source pushes the charges along, right, and they rearrange very rapidly to cancel out the fields. Most of the EMF, if you in a perfect conductor, the EMF is arising from having the source is arising from the source and going around the rest loop, not contributing much. So one of the consequences, though, is that different frequencies travel at different speeds. So that's, in other words, that's dispersion, right? We have a dispersive relationship right there. And we can kind of think of it, basically what it amounts to is the different frequencies, right? They'll have different, you'll have different allowed transverse modes, so different amounts of transverse wave vector in addition to the longitudinal, right? So we'll call this direction, whoops, not that. We'll call this direction here, that's Z, right? So with different frequencies, you'll have allowed different longitudinal modes, and it turns out so that one way to look at it is there's a solution to the wave equation in the transverse direction. Another way to look at it is there are different paths, and we can use ray optics to give us a kind of a sense of why they're different speeds. So one path down this thing is just to have a ray that goes, whoops, like that. But here's another path down this waveguide. You could do something that goes, so even if the speed of light in vacuum is the same, it's this one right here, this ray will take a different amount of time to reach the end, right? Because effectively it's like a longer path, right? Really it's actually just one wave traveling down the waveguide, but we can simulate it with an array that does that, and we can go even more extreme. You could have an array that does something like this, right? Oh, you can't see that, right? Bounce, 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 bounce. And so that's going to have even slower speed. Yeah, exactly, right? So, and so you could actually hear this if you ever go to a pipe going under the road, a culvert, or you just have a long pipe, PVC pipe, metal pipe, something like that. So either a culvert passing under a road or a PVC pipe or metal pipe. If you make some sort of a quick abrupt sound, like clap your hands, right, or snap your fingers, or even just bang on the side, right, that quick short impulse, in order for it to be a short in time, it means it's got to have lots of different frequency components present. And so what you're going to hear is you hear something that kind of sounds like boom, boom, even though as like an echo. Like you go, and as part of it, right, the echo will be very, very, unless it's really, really long, the echo will become really, really quickly after it. But so at the tail end of your snap or clap, you'll hear kind of a boom, and that is a chirp, right? The frequencies are traveling down to the end and reflecting off of the end, because there's what we call an impedance mismatch. They reflect off the end and they travel back. But the different frequency components take different amounts of time to travel down and to travel back. And so you hear the frequencies separated out. So that's called a culvert whistler. And so you can understand it qualitatively using this ray optics point of view picture. To actually understand the speeds quantitatively, we have to do the full wave equation treatment. Here, so let me snip this and show you some of the longitudinal modes. Do I have another one? Okay, yeah. All right, so let's see if I can share this one nicely, though. Oh, one moment, bear with me. Okay, so this is going to be looking this. So that left to right is down along the pipe, and up down is the transverse direction. And here we go. Share. So these right here represent. So this is a rectangular waveguide for the first two rectangular ones, and the bottom is a circular one. So here's the cross-sectional view of each of the three, and then here is a cross section, but where this direction, like left to right, is the longitudinal direction. So we're just seeing only one of the transverse directions visible right here. And so we label the modes a couple different ways. We would label them whether their fields are either the electric field is transverse or the magnetic field is transverse. And you can have, so our regular waves in empty space or in areas that aren't confined, basically in other materials, are transverse electric and magnetic. So those would be called TEM waves. But it turns out, if you reaction, it turns out mathematically in a purely empty waveguide, so nothing like this, you cannot have TEM waves. You can have either transverse electric field, but not transverse but some longitudinal component of the magnetic field. So it would be a TE wave, or you can have a transverse magnetic field, but some longitudinal component of the electric field, and that would be a TM wave. So in order to support in a waveguide, you could also have a waveguide where there was a conductor right in the center of it too, in addition to the walls. And so in something like that, then you can have TEM waves as well. And again, this has to do with solutions to our wave equation. So here we can see in this one, the electric field, the red, right, is going left to right, and you got up and down magnetic field, but the magnetic field also has some longitudinal components right here. But the electric field we can't see because it's purely transverse, so it would be coming in and out of the plane towards us, and so we can't see those end on. Likewise, right here, right, for electric field has some longitudinal components, but the magnetic field is purely transverse, so purely in these planes. They did draw them here.
What about the boundary conditions for T10 for E?
So for this one right here, right, you can have an electric field perpendicular to the wall. You can't have it parallel to the wall. So here, these right here are perpendicular to the walls right here. It's not parallel at the boundary. So these right here, notice the field is getting weaker. So right here, the field goes to 0, but it's strongest in the middle. Then drops off to 0 right at the walls. Right.
All right, got it.
So what was I going to say with these? Oh, and so these labels 1 and 0 and 1 and 1, this refers to the modes in the two different directions. So basically, is it the lowest mode or the first mode or the second mode or the third excited mode? So basically, excitations get shorter and shorter and shorter, just like standing waves on a string, right? They get shorter wavelength with more and more oscillations in them in different directions. So here, right, you go, yeah, and so that's the origin of these labels. And yeah, well, you could read more about it. So I'm going to flip over to a different view quickly. Here are some more in a circular waveguide. Here are a bunch of different transverse modes, but also some hybrid mode. Yeah, what uses does one mode have over another? First of all, spatial distribution. The different modes, you can only a certain allowed frequencies. The cutoff frequency below which you can't operate changes, right? So what causes a difference in the mode? So one thing is the frequency and what's the combination of the longitudinal wave number along with the transverse wave number. So the transverse wave number will give you basically how many, how many times you have maxima and minima in the transverse direction. And then longitudinally, that gives you more wavelength as a wave propagates down the tube. Yeah. So why are these things? So what uses do they have? So first of all, the different speeds for the different modes, different and different dispersion relationships, different cutoff frequencies, and different spatial distributions. But you can see you get all kinds of different patterns here. All right, let's do this one, and then I'm going to show you something that actually has to do more with like fiber optics and optics. So instead of showing field lines, let's look instead at just intensity, a map of intensity, right? So instead of having field lines here, we have got something where it's brightest in the center and just dies off right here. Or here, right, there's a 0 at the center in this direction, but it's brightest in the left-right direction, there's a 0. So there's 2 lobes to it. And then, but it gets stronger and stronger, brightest as you go vertically, and then weaker and weaker and weaker again, like that. So here again, we're looking at intensity. This could be intensity in just electric field in a regular microwave or something like that. But very often, right, these are the kinds of modes looking at with light in fiber optics. And so, yeah, if you want to have a nice laser beam coming out, normally what you want is what's called a single mode fiber, where you can't have any of these other ones. All that's supported is the very, very lowest mode right here. Fourth ones looks like line, yeah, a bullseye, right? And so notice as L for L equals 0, right? There's no kind of oscillations, right? In as you go around azimuth, like the angularly. There's just radial oscillations, right? And then M gives you, I'm sorry, an L, yeah. One of those indices tells you the number of zeros, basically number of nodes you have as you go around angularly, and one tells you the number that you have as you go out radially. So, and it turns out, right, you can have all these different modes, each with their own phase, and so if you overlap them, you get interference between them, and so you get even more complicated, like speckly, noisy-looking pattern. So if you send a laser down just a regular fiber, what you're going to get out is all speckly and so on, because there are a whole bunch of modes that are present there, and they're all going to interfere with each other. And as you move the fiber, that speckly pattern changes because the different modes are taking slightly different paths, is one way to look at it. If you go back to that ray optics, so as you bend it, you change the path that they take slightly, which changes the phase slightly, which changes the interference pattern. So then you have to deal with, you won't get a nice laser beam out of it. So it turns out for the fiber that you use for telecommunications, right? They want single mode fibers, but it has to be able to support a variety of wavelengths at the same time, because you can encode information in the different wavelengths. Just more recently, so you can going down your fiber, you can encode information by in different amounts of time, right? And you can interweave a couple of different messages by interweaving them in time. That's called time division multiplexing. Yeah. Exactly, right. So Harry has a question. I'll get back to that in just a second. You can also, though, send down different wavelengths and they can overlap with each other, and then you can separate them back out afterwards, and that's called wavelength division multiplexing. More recently, right, and so one of the goals people have, though, is to try to cram as much information as possible down our fiber optics so we can improve our internet speed, right, data transfer speed, because you can't just keep running. Our data use is growing exponentially, but you can't just keep laying more fibers, because that's a losing battle, right? You can double the fibers, it only doubles, the information, but we want to go up by orders of magnitude. So what you need is to take the existing fibers and find ways to send more information down them. So another thing people have started doing, though, is encoding information, sending separate messages down different modes too, and there are ways to separate those too. So Harry was asking, why is it so hard to send light down a fiber? The fibers that you've been working with, laser light, are very, very difficult because they are only single mode fibers. If you send light in a slightly different angle, right, the rays aren't going to line up straight down to give you that nice mode. What you'll get is you'll couple into one of these other modes, and those modes, though, aren't supported in the fiber, in a single mode fiber. So what that means is their K vector is imaginary, so they just get attenuated, and then they get lost. Basically, they leak out the cladding. They don't propagate down the fiber. So yeah, there's only one mode to get that light into, and so only one particular alignment of the light couples into that. So that's very, very difficult, a big, big pain. One way to do this is we can actually talk about free space modes too, and basically by looking at, well, what would happen if one of these modes traveling down the fiber leaves the fiber? How's it going to propagate? And so this alignment of your laser beam into your single mode fiber, or it could actually be into other types of confined spaces. We sometimes talk about cavities. Cavity just means the space between two mirrors, and they can be curved like this, so that only certain waves make many, many round trips within them. The only way you'll get the light into them well is if you have matched the mode of the laser light into the mode of the fiber or the cavity. If you don't, then what actually happens is, yeah, it doesn't propagate in there. And I was saying, as attenuated as it goes, where's that energy go? Some of the time, if it's like a fiber, a lot of it's just escaping to the cladding. If it's just a space between two mirrors, what happens is the light goes in and just comes right back out. It doesn't build up inside the cavity if you haven't matched the mode. Anyways, so again, wanted to show you lots of math, lots of solutions to the wave equation, separation of variables. Here we're looking just the transverse direction, but before we were looking transverse and longitudinal. Lots of technological applications. Oh, another thing, L's and M's. Do those numbers and letters those indices sound familiar from somewhere else? Where did you see L and M related for? Quantum stuff, right? Atomic physics, right? So, and that's again because, yeah, chemistry, right? That's atoms, right? And that's because, right here, we've got a circular geometry, right? And these things, don't they look like a little bit like electron orbitals in a molecule or atoms, right? Like this would be an S state right here. This looks kind of like a P state. Maybe a little bit like a D state right here, right? So L equals 0, L equals 1, L equals 2, and that's because it's the wave equation, second order ordinary differential equation, a lot like the Schrodinger equation. We're doing it in a circular, like a spherical geometry, so you're going to have the same set of orthogonal solutions to it. So again, the same math where we can solve what are the allowed modes, you can have going down your fiber, you very, very similar math to figuring out atomic orbitals. So again, this bit of abstraction allows us to come up with kind of universal patterns that makes it so that knowing a little bit about atoms can help us figure out something about the way light propagates down our fibers too. Kind of cool. That's physics, right? Okay. Let's draw a big line right here, right? Big divider. We are a little bit more than halfway through the class, period. So for the rest of today and a big chunk of tomorrow, we're going to be talking about potentials and what we can learn from them. So big jump. I hadn't meant to spend so much time on waveguides, but they're interesting. So this is beginning of chapter 10. You do not have to read all of chapter 10. Will this be on the exam? No, right? It's actually some of the stuff we do initially is actually mathematically, right? It's easy for me to write kind of short questions, but we haven't practiced it. That wouldn't be fair, so we're not going to do that. So we're going to do this in general, right? This is taking potentials and finding. So far we've been saying, okay, well, hey, let's make a few choices and then we'll work with the potential right here. But we're going to do the most general form of this, and we're going to see what can we learn and what freedoms does it give us, and then what do the different choices allow us to do. Doesn't sound very physicsy, but it actually it's very physicsy and gets into some really deep math involving symmetries and stuff like that too. But so just in general, right, for E&M, right, what was the whole point of this? Our goal in E&M in general is something like, given some charge distribution, and how it moves, so the current distribution, then I'm the electric field, and that's an R, and the magnetic field, right? Which sounds simple, but it's actually really challenging, right? So what we did is we started out with restrictions, right? Right. So simplifications. Right, and specifically, right, we said, hey, let's have either our charges be stationary or our currents not be changing, right? And that was what we called electrostatics or magnetostatics. You know what I'm trying to write. So that was fun 3, right? And then we did some particular configurations. And so now, particularly if we had more time, we're not actually going to get there, towards truly general solutions. Again, if we had a week, we could, or even a little bit more than a week, we could do it. But, or at least start in on it to see some of it. So we're just going to get a flavor of this. So it turns out that fields are actually kind of a pain. It's actually easier to work with potentials. It's also instructive. So we haven't actually done a whole bunch with them, so we're gonna do this will be like a really quick refresher, and then we're gonna see some of the implications of this. I'm actually gonna start on a fresh page. I guess I should save this too. All right. Yeah, under normal circumstances, we'd have a good week plus of this, and you could see a bunch more. Here, we're just gonna have like basically a day and change, and it'll to give us a flavor of what's going on. So here, let's start off with a vector calc. Why we have potentials in the first place. Right. So turns out that whenever we have the divergence of a vector equal to 0, what that means then is that that vector, well, we know that the divergence of a curl is 0. So that means that any vector that can have any vector that is divergenceless can be written as the curl of something else. Right. And so that was useful for our magnetos. The other thing is if our vector field is irrotational, right? Its curl is 0. Well, the curl of a gradient is 0. So any vector that is irrotational, we can write that vector as the gradient of a scalar field. And that's what we did in electrostatics, right? So let's take a look at these things, right? Let's actually do this in general electrodynamics, though. So let's write out Maxwell's equations, right? So first thing is the divergence of E, divergence all right, so now that we were writing these all the way out, we see, okay, that the magnetic field is divergenceless. That's useful, but we don't have anything that's truly irrotational. In electrostatics, the curl of E was 0. But that's no longer the case in electrodynamics. So what's the deal there? All right, well, we'll catch up to that in a moment. So let's start off with what we do know. All right, what we can do is just like before, so as in magnetostatics. Are we working in a vacuum again? Nope. Oh, yeah, sure. We're in a vacuum. All this can be generalized to situations. Yeah, yes, we're in a vacuum, but there are free charges present. But we're not in we're not going to do in matter now, just because. Yeah, this is all then generalizable, right? If we were to write out Maxwell's equations in matter, right, we would have a similar thing but this would be divergence of D equal rho free, right? And we could write curl of H in terms of J and dt. So J free and dt. So same idea, same conclusions though. So let's just keep things simpler though, right? And we'll work in vacuum, but with free charges. So this right here. So once again, that means I don't like the way I was writing that. Once again, B can be written as the curl of some function called A. which we call our vector potential. Right, same as before, but like I said, right, in electrostatics, we had the fact that the curl of E was equal to 0. And so that meant that E could be written as negative, it could be written as the gradient of some function. So let's call that function negative V, and the minus sign we can pull out. But this doesn't hold for electrodynamics. So what do we have? In fact, we've got the curl. We've got Faraday's law. It tells us that the curl of E is minus dB dt. All right. So what we're going to do here is, well, okay, let's substitute for B. Okay. And we'll see what shakes out. Right, what are we going to substitute? We're going to substitute in the equation we just, reconfirmed, that B is equal to the curl of A. So we can write this down and say that here, actually, I'm going to take this and I'm going to go up to here, right? So now we write this, the curl of E is equal to minus d dt of the curl of A, right? But I could take that and I could write that as equal to, well, okay, the time derivative and the space derivative, right? Those are linearly independent commuting variables. So we could swap there. So this becomes minus curl of dA dt. And then what we're going to do is we're going to take that term. Well, that's a curl, right? So let's take this term right here and move it over onto the left-hand side, right? So then what I'll have is a curl. I can group the curl together. Curl of, I'll have E, and then we move the negative dA dt to the left-hand side, so it became a positive when we canceled it out on the right. Positive dA dt, and then we're left with 0 over here, right? And so now this right here, right, now this looks like what we did over there. So this whole thing right here, the term in the parentheses, is playing the role of the vector v over on the left, the general vector v. Right? So what this is telling us then is the fact that we've got the curl of a function, the function is e plus dA dt is equal to 0, means then that e plus dA dt, where did I write that? No. So this v over here, I'll make a note. This is v. It's an arbitrary vector field, right? Versus the capital V that we did, say, for our potential, say, down here, right? potential. Why is that? My mouse is not following well. So happy now? The lowercase v in the upper left was our generic vector field. Cool. Yeah. Same problem. V for vector, V for capital E for potential. Drives us crazy, right? And so here, let's not come up with a new name. Let's call this one, right, a capital V, because it's still a scalar potential like that. And so, right, we can now, and then once we've done that, let's take this A potential and move that back over to the right-hand side. Right. And if we do that, then we can define our electric field in terms of our potential. Our electric fields, we have the minus gradient of V, just like before, but we also have minus dA dt. So that is box-worthy. Wasn't he a stand-up comedian that used to tell Joe redneck physicist, Jeff Boxworthy? Anyways, so note over here. Yeah, right. Right. So first thing is, right, we can recover the static case. And right, that's going to give us a dB dt equal to 0 too. Right. And yeah, so like, was that Harry who commented? Or was it Nick? Or was it someone else? Harry, who commented, right. Right, it's a coupling, though. That was supposed to be a dB dt that you're pointing at. Right, so if your dA dt is equal to 0, dB dt is equal to 0. Oh, and if dB dt is equal to 0, right, why was I talking about that? If dB dt is equal to 0, then over here, can you see a pointer? I'm not seeing a pointer when I do this. I'm pointing at Faraday's law, right? If dA dt is equal to 0, then dB dt is equal to 0, and when dB dt is equal to 0, then the curl of E is equal to 0, and we get, all the electrostatics. So, but we get the coupling between basically what was the electric and the magnetic potentials, right? Our electric field now also depends on A. Cool. All right. So let's actually see what this tells us. But let me retain this first. Okay. So let's take this and substitute it into Gauss's law. We're going to see what this new potential formulation tells us. Right, so Gauss's law, here, I'm going to write it out. Whoa, I need the derivative first. Here, I'll put the field in parentheses so we can see really clearly where the substitution happens, right? We're going to substitute in our potentials for E. So we're going to take the divergence of minus gradient of V, our scalar potential, but then minus dA dt, right, with our, and that's equal to rho over epsilon naught. Sorry. All right. And so now the divergence of a gradient is the Laplacian. And there's a minus sign, but we're going to move the minus sign over to the right-hand side. So divergence of a gradient of V is the Laplacian of V. And then the divergence, when we take the divergence of dA dt, again, what we do is swap the order of the derivatives. So this becomes d dt of the divergence of A, right? And I said that minus sign on the left side, I multiplied through by -1. So this becomes negative rho over epsilon naught. Okay. The vector, yeah, it's because think of it this way, right? It's a del operator dotted with a del operator. Del dot del, is my pointer showing up? Here, somewhere like this. Del dot with del, right? There we go. And so what you get, so then you get, so what would happen if I had, I'll do it over here for a second. If I had, let's call a lowercase vector a dotted with lowercase vector a, right? What I would get in that case would be the magnitude of a squared, right? So the same thing, we're doing something similar, right? We don't retain any vector nature. Yeah, right? It's really, right, the del operator is x hat ddx of whatever's going to come later, plus y hat ddy, plus z hat ddz. When you take the dot product with itself, you get the ddx squared plus the ddy squared plus the ddz squared. So it's d squared dx squared plus d squared, right? And that's Laplacian. Yep. So it makes sense if we're treating these as operators. D, 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 B, D, B, D, B. Yeah, I know. That's why I prefer to, I prefer to refer to them by what they mean instead of just literally reading them, because then it really does sound kind of a lot like D, D, B, D, B, D, D. And the whole point of using the symbols is to convey meaning, although they're there so we don't have to, so we can basically compress and be precise yet succinct. Anyways, this is a useful equation, though. If you look at it, it looks like Poisson's equation. And in fact, we recover Poisson's equation when we've got static fields, when the time derivative of the divergence of A is 0. All right, so we've got one of the cool things about this is it's all in terms of potentials. And it contains the info. We started with Gauss's law, but we use Faraday's law too. Okay. Here, I'm going to snip this, and we're going to do the same thing for the other two laws. And that will be, then we'll be out of time. And we'll see what the implications of all that for part of our next class. Can you still hear me? Is the connection okay? It's telling me it's not good. Fine here? Okay. Okay. Video as in like the camera versus the, or is the whiteboard also coming in and out? Okay. So aside from my gestures, though, that's less relevant. All right, we're going to do that. So, right, Ampere, Maxwell laws, curl of B, U naught J. Yeah, little tiny face. Right, and so we're going to substitute in for B and E. So I'm going to write this out as curl of B is the curl of A. Curl of A, right? And that's equal to, I'm going to leave the mu naught J alone. And then plus epsilon naught mu naught, and our E is negative gradient of V minus dA dt. So the next thing is we can use a vector identity. The curl of a curl. You can get this, derive it if you treat the del as an operator. You can treat it from the triple cross product too, the back cab type stuff, but you have to be careful. So you could also just say, hey, I'm going to look this up in the front cover of Griffiths, this vector identity, and it's the gradient of the divergence minus the Laplacian. And then here, let's separate this out. Minus naught, u naught. Oh, I left out something right here. What happened to the time? Exactly what Harry said. I left, this is d dt up here, and I'm going to fix that parenthesis. Happier now, right? And so that's going to be key, right? So over here, oh, and in fact, right, as before, as we've done many times before, we can switch the order of our temporal and spatial derivatives. Right, and then here we've got ddt. We've got two time derivatives. Cool. So, okay, we've got a bunch of places where we have two different derivatives, right? Second derivatives, and here's two derivatives, and here's a second derivative right here, and then and a cross derivative. So what we're going to do is we're going to gather together all of our second derivatives and all of our cross derivatives. Here, let's just write that out. Gather second derivatives. Respectively, right? So three different groups. Right. So first thing is we've got, and I'm going to multiply through by -1, just, to keep things clean. So Laplacian of A, right? And then we also have that temporal derivative, which I multiplied by -1 through by -1, so it became positive. But then when I move it over to the left side, it becomes negative again. Right. So that's one. After, oh, okay. Well, luckily, I'm hoping that this records this way, the way I see it. Everyone's still seeing it, so hopefully it'll still record this. So if you need to, you can go back and watch the last like 1 minute and change. Um, all right, so here are we've got a couple places where we've got the gradient of some other thing that has derivatives. So one of the things is the divergence of A, and remember I multiplied through by -1, and then on the other side I multiply through by -1, but I pick up the minus sign again when I move it to the hand side. So the gradient of dv dt, and then let's keep this. We multiply through by the -1 again. So this is our source term, which we're keeping by itself, becomes minus mu dot j. So again, right, it's all in terms of potentials. Oh, so this, not particularly pretty, but I'm going to put a box around the whole thing. Oops. Let's see if I can do it this way. Whoop. That is ugly. I'm going to undo that. Let's do it this way. Let's put a box around the whole thing. It's a very painterly box. Freehand. All right, so it's all in terms of potentials. Majestic, yeah, it's pretty freaking ugly. Yeah, but it's nice in that it's got everything in there, and it's got all the information of divergence of B equals 0, Faraday's law. Right, the divergence of B is equal to 0 came from the curl of A. B equals curl of A. Faraday's law, ooh, that's an extra W. And the Ampere-Maxwell law. Okay, so both of these things right here, right? The point of these two equations that we did on this screen and last screen is that we've got these. This one right here also looks kind of like Poisson's equation, that we've got second derivative and some cross derivatives, so call the second derivatives also related to us. So we'll call them Poisson-like equations. So that means that if you've got V and a scalar potential and a vector potential, from that you can relate them to our sources. And with our sources, you can relate to our fields. So what we're going to do is look at the implications of writing things this way in the next class, and that's going to tell us about some new physics and some connections to techniques in other fields of physics. And we'll just do mostly a flavor of it. But that's going to be kind of like closing things up. What new physics does this tell us, and how can we connect this to the future? Cool? Oh, and I don't even know what you're saying because I'm in the middle of snipping. Give me a second. I'm hearing bing, 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 but I can't actually see it. Chat. All right. Very cool. Cool. It's a lot. You don't have to like look at all these scramble of vector derivatives and get it all right now, but it's mostly just to give you a flavor that, yeah, with this powerful abstract, we can do all kinds of stuff and extend it and learn stuff. Yeah, you don't have to get it right now. Mostly that like it's out there. We can do stuff. With more time, more study, you could do it too. Yeah, it depends, right? Different areas appeal to people differently. So it's there. Like the first step is awareness of the existence, and once you know that it's there, then the next most useful thing is knowing how to find where it is. And after that, like you can have someone else has done it. You can just use their work and recreate it and build from there. Physics of philosophy. Philosophy of physics or physics of philosophy? What is the sound of one hand clapping? Oh, wait. Okay, I will see you all on Friday. Last class. Be well. Take care. I don't know. Be a Boltzmann brain. Statistical fluctuation that just happens to have consciousness. See you.